Okay, so last time we spoke a little bit more about tensors. We put them on a basis, and then we spoke about a very special tensor, a 0-2 tensor that we called the metric tensor. And we had some properties of the metric tensor, namely that it was symmetric and that it mapped the vector space to the vector space to the dual space, and that it was non-degenerate. And I gave those definitions rigorously in terms of the terminology and the notation we've been using. What I now want to do is I just want to give you a very simple example of how the coordinate transformations for a tensor work. Remember, I said if you're given the coordinate transformation, then you compute the Jacobian, you compute the inverse Jacobian, the vectors transform with the Jacobian, and the dual vectors transform with the inverse of the Jacobian. And so you can actually take any tensor quantity in one chart and get the components in an additional chart. Okay, so let's just have a look at how it goes. And we're going to start with a very simple, flat, two-dimensional metric. Okay, so what we then have is just Pythagoras. So we have ds squared equals to dx, the first coordinate squared, plus a second coordinate squared. Okay, so that's just simple Pythagoras. And the components of our metric, remember, it's basically a matrix. ds squared is g, let's say, ab times dxa dxb. So it's basically a matrix, the metric, and from this ds squared equals to that, you can immediately write it down that it's the diagonal matrix. Okay, so it has two elements, and the off-diagonal elements g1, 0 and 2, 0, 2, 1, sorry, d1, 2 and 2, 1 are 0. Okay, so that's our representation of the metric in terms of the coordinates x1 and x2. Okay, so what I'm now going to do is I'm going to change coordinates to parabolic coordinates. So if, for those of you that did my PDE course, there are certain sets of coordinates in two dimensions that are orthogonal to each other. And remember, we derived them from a complex equation, and one of the ones were basically the parabolic equations, where you have xc1 going from minus infinity to infinity, and xc2 going from 0 to infinity. And the transformation, if we actually write it out, looks something like this. So it's not pretty. So we have xc1 equals to the square root of x1 squared plus y1 plus x2 squared plus x1, and xc2 equals to the square root of x1 squared plus x2 squared minus x1. Okay, so that immediately gives our barred coordinates in terms of the unbarred coordinates, if we follow the notation from the previous lecture.
Is there a certain way of rule or something special going on that the other one does not have a plus or minus, or is it there is plus or minus? There's nothing special there.
No, it comes from the coordinate transformation. So that's just given.
Okay.
I'm not sure. You'd have to check the coordinate transformation. Okay. I think what usually happens is one acts slightly like a radius, another one. I'll show you a picture of the coordinate transformation. And the other one acts like an angle.
Okay.
Usually with these, but I will check. I'll see when I draw the pictures now. Okay, so then what you can do, in this particular case, it's possible. It's not always possible to get the inverse transformation. So here we can get, if we're given the transformation of the barred coordinates, which I've called xc, as a function of the original coordinates x1 and x2, I can now get the inverse transformation explicitly, and what it is x1 is just a half xc1 squared minus xc2 squared, and x2 is xc1 times xc2. Okay, as I said, this is not always possible, but if it is, it's useful to check. If it isn't possible, you can still do the calculations by computing the Jacobian using this thing and then computing the inverse Jacobian to get all the transformations. Okay, so now what we're going to do is, remember I said we compute the Jacobian, which is the derivatives of barred coordinates with respect to all the possible unbarred coordinates. So we get the C1, the x1 is just this thing, and we are wanting to write everything in terms of the new coordinates. So even though we take the derivatives with respect to x1 and we get an expression with respect to the old coordinates, we always want to go in and actually get the final expression in terms of the new coordinates. Okay, so we basically do this and then we observe that this thing on top is just c1, and x1 squared plus x2 squared you can simply get by squaring this thing and squaring that thing and adding them together. Okay, so it's c1 over c1 squared plus c2 squared. And be careful with the notation, because when we're working with several coordinate system, we don't want to call them x, y, and z. We've simply called the different coordinates x1, x2, and x3. But then when you add a square, I tend to put brackets around the coordinates. Okay, here's dx1, dx2, also just differentiating this thing with respect to x2, and then once again I write it as xc2 over, I simply use expressions for these guys and I write it in terms of the new coordinates. And we can go on, do the same thing, dx2, dx1 is just minus xc2 over the squares. Dx2 dx2 is also equals to just xc1 over the squares. Okay, so this sorry, this is our Jacobian. Okay, then we want to compute the inverse Jacobian, and we can either go to this transformation, or as I said, we can just view this thing as a matrix and work the inverse out, the inverse matrix. And the first time you do it, it's very good to do both. And in fact, it's a check. If you actually can find an explicit inverse transformation, compute its Jacobian this way, and then multiply the two together and make sure you get the identity matrix. Okay, so here we go. dx1, dxc1 is just c1. dx1, dxc2 is just xc2, and dx2, dxc1 is xc2, sorry, the previous one was minus, and dx2, dxc2 is just xc1. Okay, so here's the inverse Jacobian, this is the Jacobian. If you multiply the two together, you get the identity matrix. Okay, so just check that. So now what we want to go and do is we want to use those transformation laws that we had for tensors previously. And we want to go and we want to transform this metric that was the diagonal metric in flat space into a metric on the parabolic coordinates. Okay, and then so here we have it, G, V1, V2. Remember we wrote out the definition, it's the sum over all the components of the previous metric, each one multiplied by the Jacobian. Okay, and in this case, because the indexes are down, you want the inverse Jacobian. So it's dx mu, dx mu1 bar. Okay, so be very, very careful when you do a transformation that you are using the right Jacobian, and be very careful, go back to the definitions from the law or the things I derived in the previous lecture as to which one, whether you taking the derivatives of the coordinates with respect to the barred coordinates or the other way around, because your covariant and contravariant components always transform differently. So sort that one out. Okay, so and in this case, we can write down the new metric in terms of the metric in the previous coordinates times these two inverse Jacobians. Okay, and we're summing over components in your metric. So we're summing over V1 and V2. So let's just see what that means. It basically means that G bar 1, 1 okay, is summing over G mu1, mu2, but the 1, 1 comes in here at the bottom. So it's taking the derivatives with respect to the first transformed coordinate. Okay, and so what we basically do if we go and write that out, that simply equals to G11 times dx1, dxc1, dx2, dxc2, that's the first term, plus G12 times dx1, dxc1, dx2, dxc2, plus G21 dx2, dxc1, dx1, dxc1, plus G22 dx2, dxc1, dx2, dxc1. Okay, so this is just an example of, in 2 dimensions, how explosive these expressions actually become. Okay, and the first time you should do it by hand, but very soon, eventually, you start using a computer algebra thing to do the algebra, otherwise you make mistakes. Or in fact, I still do things by hand because sometimes I can see simplifications that Mathematica can't see, but then I at least go and I check it with some computer algebra program. Okay. So let's just substitute in the values. G11 is 1, dx1, dxc1, and is simply xc1, so that's xc1 squared, that's the first term. G12 is 0, G21 is 0, G22 is 1, and then you have dx2, dxc1, which is xc2, so there's that one squared. Okay. And so our metric components for G11 is simply in the transformed coordinates, it's xc1 squared, xc2 squared. And you can go and you can do all the others simply by changing these indexes below. Okay, so from the point of view of the underlying things that led us here, that takes insight, but when you actually get to working with the things, it's a very straightforward application of the transformation rules if you go between coordinates. But the power of it is to know that those transformation rules are actually describing entities that exist independent of coordinates. Okay. You just have one representation on, in some sense, for the metric on Cartesian coordinates, and then you have another representation for the metric on your parabolic coordinates, but it is the same metric, it's the same tensor. They both describe an intrinsic idea of distance on, in some senses, manifold, and they both, in fact, describe a flat space. Okay, and we'll see how we start seeing when we don't describe a flat space 2 lectures from now.
Yeah, but I can see there are only zeros there. That means we followed conical through because of V1 and V2 are not equal. Hence we have 0.
What do you mean V1 and V2? Oh, when V2, you have zeros. So this is a property of the fact, remember I looked for all coordinate systems that remain orthogonal when I derived these parabolic coordinates for you in PDEs. Okay, that's a sign that they are in fact orthogonal. They're diagonal. That need not have been. I could have chosen any coordinate transformation. I could have said xc2 is x1 times x2, and xc1 is x1 times x2, and xc2 is x. Okay, you can do that transformation, an easy one. You can work it out, and what you will then get is that your diagonal elements are not 0. Okay, it's only in orthogonal coordinate system that the diagonal elements remain 0. Okay.
Okay, so obviously if you don't have the inverse transformations, then you just get your Jacobian from the blue ones, and then you get the inverse.
Yeah.
And
then you have your other one.
Yeah, and that's all you need.
That's all you need, and then you can transform it there. So very powerful, and you'll see later on we're going to start writing down equations in tensors, and those equations will be the same equation whether you're in this coordinate system and in the other coordinate system. Okay, so in some sense, yes, it's hard to transform between the two, but in some sense we are going to get a representation of equations on a manifold that doesn't depend on the coordinates you're actually in. Okay, so just if you actually wanted to look at the coordinates, remember I said, yeah, this is why it's plus, okay? Like C1 goes from minus infinity to infinity, and C2 goes from 0 to infinity, so that's why it's just plus. And if we actually wanted to look at what the coordinates did, so if we look at a grid like C2 goes from 0 to infinity, and C1 goes from minus infinity to infinity, and you can see these lines are colored. And if you now use the transformation and you put these lines of a constant C1 and constant C2 into our Cartesian coordinates, then this is what it looks like. So you can see here's the green line, okay, and that corresponds to that parabola. Then you have this line, and that corresponds to this parabola over here. And you can sort of see all the rest. So this is, remember we had a problem that we had an aircraft wing or something, and then we wanted to use coordinates that were constant with the boundary of the aircraft, and this is where the parabolic equations actually, or parabolic coordinates come from. Okay, just one more thing. Remember we also in the last lecture said that if you have a metric, you can always get an orthonormal basis to the metric of unit vectors that are orthonormal, that are not necessarily a coordinate basis. Okay? And in this case, you can always write the metric that way. Let's just see what that basis actually does. Like in this case, here is our new coordinates. Okay, a orthonormal basis would just be U1 and U2 that in some sense are diagonal. This is possible because the actual metric itself is already diagonal. Okay, so the eigendirections of the metric simply point in the C1 and the C, or tangent to the C1 and the C2 curves. Okay, so those orthonormal vectors that are associated with a metric in the parabolic coordinates are these two. I called them V, I think in the previous lecture. Here they are U. Okay, so just one more thing. The coordinate basis for VP is ddxc1 in the parabolic coordinates and ddxc2. And they are orthogonal, but they're not orthonormal. Okay? The orthonormal vector basis is U1, which is simply ddxc1 rescaled, so that when you have U1 dotted with or applied the metric to it with another U1, you're going to get 1. And U2 with ddxc1 squared plus ddxc2 squared times ddxc2. So the orthonormal vector basis is often different from your coordinate basis. In fact, if you have a metric that is not diagonal, then it's going to be a combination of your coordinate basis. It's going to be basically the point in the eigenvector directions of that matrix, your orthonormal basis is. And then the eigenvalues are going to rescale them so that they are actually unit vectors. Just another thing, this matrix, because even though it is, its components are not on our functions of C1 and C2, its signature is +1 +1, because if you take the norm of U1, U2, or you put, say, GU1, U2 in there, you're going to get a plus. And GU2, U2, U2, you're also going to get a plus. Or you could go equivalently. Remember I said the signature doesn't change depending on your chart. You could go just straight back to the original metrics, the original metric in Cartesian coordinates, which was 1, 1, and you would get plus, plus. Okay, so I hope this example at least illustrates a little bit yesterday's lecture.
Yes.
Okay, go through it carefully, but stick rigorously to the notation that was actually given in yesterday's lecture with the transformations. In tensor analysis, it's all about precision. Don't mix up your indexes, don't swap top and bottom, know which coordinates are barred, know which coordinates are unbarred, and then you're fine. Okay, so what we're now going to do is, this is actually how I learned tensors when I started. I learned it as a machine that if I follow the rules, then I always get the right answer. And the stuff underneath, like the way it's been systematically developed using maps and only introducing the necessary thing when you need it and sort of structuring together, becomes valuable later on, especially if you want to actually solve the field equations, knowing how those things fit together. Initially, for working examples and just working with two-dimensional things, this abstract index notation is fine. And in fact, I think in the course in Stellenbosch, I kind of start here. But I did want you to see the underlying structure of the manifold developed. Okay, so what the abstract index notation does is it actually mirrors the component notation. Remember, we had our idea of a tensor as a multilinear map. Then we said we were going to work out the basis as a combination of simple vectors, simple basis vectors from the dual space and from the vector space, and we can make all our simple tensors that way. And then we said, fine, one-way representation of the tensor is the components times the basis. And then that thing works so powerfully or so easily if you just keep track of the indexes above and below, and you can do contraction, that people went on and said, let us rather represent the whole tensor, even if we don't know what the basis is explicitly, using abstract index notation. Okay. So what it does is basically mirrors component notation without explicitly introducing a basis, and it makes it a lot easier when we compute quantities. Okay, especially when we take contraction and when we take the exterior product of the thing. And it also makes it easier when we keep track of slots. So up until now, we've sort of said G of 2 operating on, say, 2 vectors gives you something. Now what we're going to do is we're simply going to use the abstract index notation. So it has rules, okay, and this is why I said there were rules that I used to just follow, and it used to work beautifully. And once I'd learned the stuff doing elasticity, I actually came back here, nobody else knew tensors, so I could get a lot of the calculations done faster. So the abstract index notation works like this. Suppose we have a tensor with k basically covariant and L contravariant indexes, and we donate, then we're going to say, okay, fine, that's a tensor, and we're going to basically say, so it's represented as T followed by the k contravariant indexes. I think I said it wrong the way around just 2 minutes ago. And the L covariant indexes, okay? And so what's going to happen is I'm going to represent this tensor, even though I don't give you the chart or the coordinate basis, simply as T followed by K indexes that are up and L indexes that are down. And so, for example, if you get an expression like this, and you don't even get a basis, you get T, A, B, C, and D, E, it simply denotes a tensor of type 3, 2, with 3 contravariant indexes and 2 covariant indexes. Okay, and so what the indices do is they help denote the number and the type of the variable the tensor acts on. Okay, and not the basis components. Okay, so these are simply another way of representing our tensor without having the basis itself. Okay, so now we can start using this to write down equations. So in equations, the same letter must be used to represent the same slot. So remember our tensor was like a function g of so many covariant indexes, comma, so many contravariant indexes. what this notation now does is, instead of having like the function with all the commas in it and stuff and viewing it, acting on stuff, it simply keeps track of what you're acting on, whether it is a contravariant index, in other words up, or a covariant slot down, and it's simply used, and this allows us to now basically write down equations, or basically both sides of the equations, if we contract things or if we increase or if we take the exterior product. And so let's see how we actually write down contraction, okay, because it's going to end up looking very similar to like taking a trace. Okay, so suppose we have contraction, okay, we're going to have the same letter, but we're going to have a repeated index on contracted slots. So say, for example, if we have this expression, we've contracted B and B, so we simply summed over those slots. And so this thing actually represents not a 3-2 tensor, but a 3 minus 1, 2 minus 1 tensor. Okay. And if you were to view this thing, say example, you would have to have TAA, you would simply have a scalar because you have contracted a contravariant index with a covariant index, and that's exactly the same as taking the trace of a matrix. Okay. So contraction with respect to the second contravariant and first covariant index. And the outer product, what we do is the product of letters, and we're going to simply drop the fact that we have this outer product sign. And so, for example, we're going to have something like this, where we have T, A, B, C, D, E, S, F, and G. It's the outer product of two tensors. Okay, and that tensor is a type 4-3 tensor. In other words, 4 indexes on top and 3 indexes below, and it simply means you multiply the things in those slots. Okay, so this is basically the tensor obtained by the outer product of T, A, B, C, D, and S, F, G. Okay, so in some sense, using this abstract index notation, even though you don't have the basis, is a much more intuitive way of thinking about the tensor. Okay. Questions here? No. So now, let's go back to the metric. Remember I said up until now, both the vector space and the dual space were vector spaces. The vector space at a point P was associated with the directional derivatives. The dual space was simply a map from the vector space to R. And we then showed that it also had the same dimensionality, and it had a basis that we could define if we knew the basis of the original vector space. Okay? And the way we defined it was simply that the basis vectors acted on, or the basis vectors of the dual space acted on the vectors of the original space, such that you basically had a delta function, delta 0, 1. In other words, the first component of the dual vector basis took the first component of the vector basis to 1, and all the others to 0, and so forth and so forth. And then we introduced the metric, and what the metric did is it actually allowed us to get a direct map from this to there without necessarily having, you always have, the metric permitted us to have a direct map from our vector space to our dual space. And what this also does is it allows us to transform contravariant, or rather covariant indexes into contravariant indexes, and the reverse. Okay, so how does this work? Suppose we have an element of our vector space, okay, and we then use our abstract index notation to work out the following thing. We say GAB times VA. This is a contraction, so this actually represents a T2 minus 1 lower index, 1 minus 1 upper index thing. So it's basically just an element of our dual space. Okay, so you can see now here with this expression we simply have G. It's almost like a matrix multiplication, but we are summing over one contravariant and one covariant and one contravariant index. And so we are left with simply one covariant index, and that's an element of our dual space. And there's an implicit sum, like we sum over all those indexes that are there. Okay, and now what we also have is the representation of GAB that are just the covariant indexes, two covariant indexes. We said one of the conditions on our metric is that it's non-degenerate. And the moment you have the non-degenerate metric, you basically can get the inverse of that thing. Okay, so the inverse of this metric is basically something that's an element of two up indexes or two contravariant indexes and zero covariant indexes. And what we call it, we donated G minus 1 AEB. Okay. So if you are given the metric, which is usually the metric that is associated with the measurement of distance, always has the lower indexes. If you take the inverse of the metric, then you basically have G minus 1 AB. You basically get a representation that you write this way that now has up indexes. Okay. And by definition, what you're going to get if you take the contraction of GAB and GBC, so you're summing over the B in the contravariant slot and the B in the covariant slot over there, you're going to just get the delta function AC. Okay, and these expressions are actually extremely useful. This one where it raises and lowers indexes is useful. This time where you multiply the two metrics together to get the delta function or the Kronecker delta thing with one covariant index and one contravariant index, that's also very useful. And a lot of equations we can actually derive, or results we can derive just by following these rules. Okay, so this thing is actually the delta AB is the identity map of the vector space to the vector space, right? Because it basically takes one vector just back to itself. Okay, another thing is GAB takes elements of your dual space and it makes an element of your vector space. Okay, so in some sense it's the same quantity. Here you have a covariant index down, you hit it with the metric, so you're summing over the index, and the result is a contravariant thing with the index. Okay, you're starting to get a feel for the power of these rules. Okay, they are going to make a lot of calculations possible. Okay, so now let's just look at a more general example. Suppose you have a tensor that's TA up, B down, C, D, E. And important, keep the order of the slots correct, okay, because that's basically different components of your multilinear map. Suppose you wanted to raise the index B up, okay, and you wanted to lower the index D, okay. What you would do is simply, if you look at this expression now, we have TA, so A has remained unchanged, and C has remained unchanged, okay. But what we have done is over here, I have said that the B is the lower index B over there, and what this GHB does, it takes that higher index up there, the H up there, and it lowers it down to give you TB. Okay, and now the second one, this GDJ, okay, it's up. The only index that you're not summing over is D, and you're using the sum over the J index over there to raise this index up to be D. Okay. Questions? Petrus, you look confused.
I'll just have to go over it.
You'll have to go over it slowly, but it's literally whenever I want to lift an index, okay, or say when I want to take this index j and I want to raise it up, then I hit it with a metric or the inverse of the metric dj, okay. Then I sum over the repeated index, and what then the lower index gets the index, the free one up there, and that is equals to d. Okay. And the same over here, if I have an index that's down, an index that's up over here, and I want to lower it, then I simply hit it with a metric. I sum over the index that I want to lower, so I'm summing over h, and then the free index in the metric is b, which is what's the one sitting over there that I've lowered it from with. And I've put up your next problem set. Take a look at it. Right at the bottom, the last problem, there are a couple of examples. Try them, and if you're still unsure, come and ask me before you hand it in. Okay, then you can at least, but go very carefully. All the rules you need to lower and raise things in are basically these properties of the metric that are given here. Okay. And you know what the inverse of the metric is. It's simply get this matrix this is just a representation, but get the metric on some basis, work out some coordinate basis, work out the inverse, and then you have the upper one. So once you have the metric, you can compute this thing and you can actually do all these calculations. Okay, so we have another, remember I said the metric also maps our vector space to the dual space. Okay, so it raises and lowers. I think I've got, this is just the same. Okay. Why is it? Okay, so this is just another example. So suppose we have a tensor TAB and we want to find its relationship to the tensor TDC, then we can simply hit GAD, which will lower the first index, and GBC, which will lower the second index, and call it B. And so that's another example. And so that's basically an element of a 0-2 metric. Another very useful operation on the indexes is this identity map. Okay, so suppose you have delta CA, okay, and this delta, the identity map, always has one index up and one index down. Okay, and so that basically means call whatever C was A. Okay, so then you have TAB. Okay, what is now also possible with tensors is that you can decompose them into parts that transform differently, just like we can decompose matrices into symmetric parts and antisymmetric parts. We do the same thing with tensors. So we can say a tensor TAB is the sum of its symmetric part and the sum of its antisymmetric part. Okay? And by the symmetric part, I basically mean you take the original tensor, you multiply it by a half, and you add TAB plus where the index is switched. Okay, so be very careful. In general, the ordering of where your slots are very important. Okay, TAB is not equal to TBA, just in the same way that an ordinary matrix is not always symmetrical. Okay, but if you have a tensor and you want to get out the symmetric part, then you can, this is what the brackets does. If you want to get out the antisymmetric part, these square brackets basically mean a half TAB minus TBA. Okay, and now another thing is, say for a tensor of type 0K, we can go and generalize this even further. We can say, let's have a totally symmetric part of the tensor. And the totally symmetric part, we tend to express in the following way. Okay? So suppose you had TABC, you can just see that the totally symmetric part is you simply add all the permutations of A, B, and C and divide it by the number of permutations that you have. And this is exactly what I've done over here. So T, A, B to K, what it means is the sum 1 over K factorial, which is basically the number of possible permutations of these indexes, of T with a given permutation. So what this pi means is basically, or what this expression means is basically sum over all the permutations pi of 1, 2, 3, 4 all the way to K. Okay, so I'll write out an example now, but just to get the antisymmetric part as well, it's also sum over all the permutations of permutations pi of 1, 2, 3, 4, but we multiply it by this funny delta pi thing over here, which I will define in a moment. Okay, so what this delta pi thing basically says is it's 1 if you have even permutations. In other words, you maintain the order. Like, for example, an even permutation of 1, 2, 3 is 2, 3, 1. Sorry, 1, 2, 3 is 3, 1, 2.
Oh, yeah, this is Levi's semicolon.
Yes, we're getting there. Okay, so if it is, yeah, we're getting to Levi-Chebet. So if you have this delta pi, basically you have even permutations, it's 1. Okay, so if you have suppose you have 1, 2, 3, it's 1. If you have a 3, 1, 2, it's also 1. If you have 2, 3, 1, it's also 1. Okay, but it's -1 if you have odd permutations. So an odd permutation of 1, 2, 3 is you just switch to the indexes. So 2, 1, 3 would be an odd permutation. Okay, so let's look at the next up, one more complicated than just 1, 2. Suppose we have 1, 2, 3. Okay, then pi, all the possible term permutations of 1, 2, 3 are basically 6. Okay, and that's why you divide by 1 over basically 3 factorial, you're dividing by 6 in this case. So you're dividing by the number of permutations that pi has, that's contained in pi, and then what you do is into each of the index slots, you first put this thing, then you put that one, then you put that one, then you put this one, then you put this one, this one. So what this let's say the symmetrized expression basically means, it's 1 over 6 times T A1, A2, A3 plus T A2, A3, A1 plus T A3, A1, A2 plus T with all those slots put in. Okay, and important, this is slots, not components. Okay, and for this particular case, the delta pi, in other words, this delta pi, when we're looking at the odd permutations, is 1, 1, 1, minus 1, minus 1, minus 1. Okay, you can see all these guys, we've switched the ordering of 1, 2, 3 here, we've maintained it, and so that's what it is. So it's very easy to decompose a tensor, even a higher order tensor than 2, into its symmetric and antisymmetric parts. Okay. And once again, these definitions apply for any groups of indexes. So what you can do, for example, is get an expression like this. What this thing basically means is T, A, symmetric on B and C plus antisymmetric on D, E, and then just F over there. And so if we then, a nice problem is actually write this thing out. And so what you would simply do is you would say, fine, let's do the top part first. So it will then be a half T, A, B, C, keep that square bracket underneath, D, E, E, F, okay, plus T, A, C, B, times a half, times square root D, E, F, with those square brackets underneath. Then you go on, and for those two, you then write out the definition of the square brackets. So at least the first time you're going to do it, do the things separately. Like first write out the definition of the symmetric part, and then for each part you get, you go and write out the definition of the antisymmetric part. And then what you'll get is this. Okay? And often you have a lot of cancellation between those. So it is straightforward, but be careful. Okay? And be accurate. Tensor analysis is all about accuracy. So I think you have to go and teach.
Yes.
Yeah. Okay. I think I'm going to stop there, and then we can start with parallel transport after we come back from Potch. Cool.